a lot from him. And also, Luciano is here, and Luciano is one of my most desired guests on this entire series. Trust me, because every time when we used to think of something about Node.js, I just refer back to his book sometimes. I'm not a Node.js specialist or else a professional who's working there, but I always believe that there is always a reason for me to look back at something which is more academic. And I think his book says a lot about that technology and everything. So I'm pretty glad that he's there on the show, educating us on all things. And over to you, Luciano, it's all yours. So we are just waiting for the knowledge to be gathered from your side.
Thank you so much. And thank you also to Cody for having me. Okay, so let's get started. So I'm going to be sharing the slides at the end of the talk. You'll get the link. So let me start by introducing myself. My name is Luciano. I am Italian, even though I live and work in Ireland, Dublin. I am a Microsoft MVP, but also an AWS certified solution architect. I actually spend a lot of my time working more with AWS than with Azure. I have done very few projects with Azure. And I work as a senior architect at this company called Theorem, and I'm going to be telling you a little bit more about the company in a second. As Vishwa said, I am the co-author of a book about Node.js, which is called Node.js Design Patterns, and written together with Mario Casciaro. And the reason why this book exists is because our opinion of JavaScript and Node.js is that it's a very powerful language and a very powerful ecosystem, but it's also very easy to do a lot of things in a bad way or write code that is very difficult to understand, or maybe not really use the asynchronous features of the language in the best possible way. So this book tries to guide you through a journey where you're going to learn all the concepts and the patterns so that you can be confident that at the end of the day, when you write JavaScript and Node.js code, that code is production ready. If you end up reading the book, please let me know and give me feedback, because this is the 3rd edition. We are always looking forward to see what can we improve for the next edition. So definitely send us feedback. And by the way, I'm also very active on Twitter, on LinkedIn. I have a blog, so feel free to connect with me and definitely ping me if you want to have a chat. Again, I'm always up for exchanging ideas and learning from each other. Okay, Theorem, as I said, is the company that I work for, and it's a consultancy company. We are AWS partners, so that's our main expertise. We help other companies to migrate to AWS, or if they are already on AWS, we help them to make sure that their deployments are as efficient as possible, as cost-effective as possible, and we help them to design new solutions, especially if they involve serverless or AI services. And if you want to work with us, either you are looking for a job because we are a fully remote company, or if you work for a company that might use us as a service, definitely, again, let's get in touch and let's chat about that. Okay, enough with the introduction. Now let's get to the topic. And I want to start this talk by describing what scalability actually means. But I'm not going to use my own words. I'm going to use the words of Werner Vogels, who is the CTO of AWS. And Werner describes scalability with this sentence. He says, a service is said to be scalable if when we increase the resources in a system, it results in an increased performance in a manner that is proportional to the resources added. So just to paraphrase what this means, we are basically saying that in a system, if we increase the resources, we are proportionally increasing the performance of that entire system. Let's keep this definition in mind, because we're gonna come back to this later on during the talk. Now I'm gonna be giving you a number of tips on how to think about performance and scalability when you're working with Node.js applications. And the first tip is establish a baseline. In order to understand what I mean by that, let's take an example application. I created this very simple example, which is an application that allows you to generate QR codes. It's literally a few lines of Node.js, but let me show you how it works first. So you have this page here where if you go to the main home page of the application, you're just going to see this text. but you can specify a query string called data and pass a value to that query string. And the value that you use here is basically going to be used to generate a QR code that contains that value. So if I click this link, this is producing a QR code that contains the word hello. But of course, we can also change the content and say, I don't know, something like hello, everyone. And that will generate a different QR code that contains the string. And you can add, I don't know, as many characters as you want to create bigger and bigger QR codes, for instance. So it can generate QR codes dynamically. That's basically the main idea. And this is just a simple application that just does some business logic every time you are sending the request. Like the actual example is not that important. It's just to have that kind of prototype of application. You send a request. Every request is different. The server has to do some work to be able to reply to that request. So you might be wondering, okay, is this application performant or not? What do I have to be worried? And to try to answer that question, let's first look at the code for this application. And as I promised you, it's very, very small. It's less than 20 lines of code. So let's see how that looks like. This is all the code for that application. And the first thing that we need to do is import a few libraries. The first one is create server from HTTP. This is a native library from Node.js core, and it allows you to create HTTP servers without using any framework. You could use Express, you could use Fastify, but for simple things, you can use Node.js core directly using this particular function. Then we are also importing an external library that you can install through NPM that is called QR code. And this library basically allows you to create a PNG image of a QR code for a given content of that QR code. Okay, at this point, we just need to use this create server function from Node.js core to basically define what is the behavior of our HTTP server. And the way this function works is that you call the function and you pass a handler, and the handler is essentially a function that is going to be executed for every single request coming into the server. And at the end, this function, the create server function, is going to return you an instance of a server, and then we just need to call .listen to attach that server to a given port. You can see that in line 18 at the end. So what we are doing here is we are just saying, create a server. I'm going to define you what is the behavior for every single request. And then the server that is created, I'm going to start to listen on the port 8080. Now let's zoom in into the handler code to see what are we going to do for every single request. The first thing that we want to do is we are going to parse the current URL. So that basically means the request that is coming in, what is the URL of that request? And we use the information from the URL. We only care about the query string parameters, and we want to look for specifically the data query string parameter. Now, what if there is no data? Because maybe you are just going in the home page of this application. In that case, we are just going to return a little bit of HTML saying, like a little bit of documentation. To use this application, you need to pass a query string parameter. For instance, you can do data equal hello, and that will generate a QR code that contains hello. Instead, if we have some data, then we want to respond with an image, and this image is going to be a PNG, and the content of the image is generated from this QR code library that can create a PNG stream, and we can immediately return that stream as a response to the user. So this is literally all the code that we have to write to implement the application that I just showed you before. Okay, but again, is this application performant? Do we know it? Can we tell by just looking at this code? Maybe if you have a lot of experience with the particular libraries that we are using, you might be able to tell maybe some pitfalls. Maybe I'm doing something wrong. Maybe this thing can be more performant. But the reality is that most of the time, you don't know if an application is performant enough if you don't actually run it and put it under stress and see how it behaves. So in order to do that, there are... Oh, sorry, I just went to the last slide. Apologies. So I was saying, in order to do that, there are a couple of tools that we can use to put the application under stress. We start the server, run hundreds of requests per second, and see how the server behaves. And two of my favorite applications to do that are, one is AutoCannon, which is actually written in JavaScript in Node.js, and it's actually very extensible. If you want to use it for more complicated business logic, you can write that entirely in Node.js. And another one is WRK, or Worker, or Work, depending how you want to call it, which is a little bit more performant, but it's written, I think, in C, so it's not as extensible as AutoCannon. In any case, what we are trying to do with these two snippets, regardless of which tool do you use, is literally bombarding our server instance with 200 connections at the same time and trying to see how the server behaves when dealing with those 200 connections, making requests all the time. And if you use AutoCannon, you are going to get output that looks like this. And if we try to understand what that means, there are a few things that are interesting. So the first thing is the average latency. So basically, we can see that on average, every single request needs to wait almost 2 seconds before they can see a response. And this is not great. And then we can also look the average of requests per second, which was about 99 requests per second. And then we can see the number of bytes per request. So what we could tell from these numbers, again, it's always very relative because it depends what are the targets for your application. But instinctively, what we can see is that this application is not performing amazingly well because every user has to wait for about 2 seconds when the system is under load before they get a response. And we are not able to process more than 100 requests per second, which is not a lot of requests. So the first tip is basically try to do this exercise where you take an application, you put it under stress, and you try to look at the numbers to understand, okay, should we do better? Is this good enough? And there is a next sub-tip that I like to call tip 1 bis, which is basically find your ceiling. And that's the ceiling. What I mean by that is basically what is the simplest piece of code that we can write in Node.js to implement an HTTP server to see in our current machine how fast can we possibly go. And here what we are doing is effectively an hello world. So this is the simplest type of HTTP server that we can write. And then if we run the same benchmark again, what we can see is that this time the latency is much, much lower. It's 2.71 milliseconds. We can deal up to 33,000 requests per second, so way more than before. And we are also able to transfer a lot more data per second because, of course, we are dealing with more traffic. So this is just to give us a feeling of, okay, our application is very specific. Of course, it's doing a lot more than just a simple hello world, but how much of our potential are we actually using for this application? So having this idea of a ceiling gives you a reference for how fast could you possibly go just by using the performance of your machine and the Node.js runtime. And again, this is not, doesn't mean that we can reach this level because, of course, we are implementing more complex business logic, but gives us an idea of what is a good reference, what is the maximum speed that we could possibly have if we were doing the minimum amount of work. Okay, now that we know what is our starting point and more or less we know how fast we could possibly go if we were doing something very, very simple, the next thing that we should do is to try to start and find what are the bottlenecks of our application. And if we can find the bottlenecks, then of course we can start to improve the performance by working out the bottlenecks first. And one tool that can help us a lot is this tool called Clinic.js. And I'm not going to give you like a super complete demo. You can check out the website and there is a video that explains very well how to use Clinic.js for a real use case. I just want to give you a feeling of what you can do with this tool. And then if you find it interesting, you can spend a little bit more time looking at the website later. One thing that you can do with Clinic.js is this thing called Clinic Doctor, which works together with AutoCannon, the tool that I showed you before. But while AutoCannon is bombarding the server with requests, Clinic Doctor is actually looking at the server and trying to figure out, okay, what is the CPU usage, how much memory is being used. is going to look at the event loop to try to understand if we are doing something that is blocking the Node.js event loop. And it's also going to look at the number of active handles that are consumed by the process at that particular, while the benchmark is running, basically. And this can give you other interesting indications about things that are important to understand when you think about performance. For instance, here we can see that when we are under stress, we are almost all the time at 100% CPU usage. So that basically means that probably our server is doing a lot of CPU intensive work, which we know in Node.js is always a little bit dangerous and hard to scale. So something that we should be a little bit concerned about. Then we also see that there are some significant event loop delay. And that means, again, that there is something generally CPU intensive work that is blocking the single thread of Node.js. And that means that we cannot keep processing other requests because there is something blocking the main thread. And we can also see that there are almost always 200 active handles, which is not a coincidence. This is the number of requests that we are keeping on all the time. So that's a little bit expected. And the other thing is that the memory usage doesn't seem too bad. So just by looking at this information here, we should be concerned about CPU. And, oh, sorry again. I keep pressing the wrong button. Okay, so if we look only at this, we are concerned about CPU and not too much about memory. But how do we know which part of our application are actually the most CPU intensive, where we are spending most of the time in terms of computation time? And there is another tool inside the Clinic suite that is called Clinic Flame, which again, you can use it in combination with AutoCannon, but this time you can use it to generate a flame graph. And a flame graph is a visualization of which functions in your code and the dependencies of your code you are spending the most time when you are running the server. So in this case, what we can see is that the biggest allocation is, I think it was this function filter some path. And then this function is in a dependency library that is called PNG.js. So I didn't spend too much time trying to dig deeper, but probably if I really wanted to optimize this application, I would start by looking at this particular library, see what this library does, what that function does. And maybe I could also assume that maybe creating a PNG is not the most efficient way of creating a QR code. Maybe I can create an SVG, for instance. I could try to benchmark different solutions this way. But again, when you find an indication like this is probably the first thing you should go and look to see. If I can optimize this function, I can probably optimize at least 30% of the performance. So that's definitely the best investment of our time, rather than trying to optimize something that maybe is keeping us busy for less than 1% of the time. So this is how flame graphs are useful, to understand what are the areas where you can have the largest impact. So it's best to focus on those areas. Okay, there is another tool that I'm going to just mention, but not give you a very meaningful example, that is called Clinic Bubble, still inside the Clinic.js tool. And this one is more useful when you have a lot of asynchronous code and you have chain of asynchronous invocations. This can help you to understand what is generating other asynchronous code. So what is the chain of asynchronous events? And sometimes that way you can understand if there are bottlenecks that are not synchronous, but depending from a sequence of asynchronous executions. Okay, once you have this idea of the raw performance in terms of latency and requests per second, then you have a little bit of a more in-depth idea by looking at flame graphs and the memory footprint and try to understand how the application is actually behaving. The next question you need to ask yourself is, what are my goals? And if we want to rephrase that question, it's basically, what are we trying to optimize for? That can be, we want to have better throughput, we want to have less memory consumption, we want to have better latency. And sometimes you cannot optimize for all of them. So we need to choose. Just to give you an example, sometimes it's very common to optimize for latency and throughput by having a huge cache where we store all the previously calculated results. So if a new request comes in, you're just going to see that, oh, we already served a response for this request. We are just going to read it from the cache and send it straight away, so we don't have to recalculate everything. If we do something like that, we're basically trading off memory for latency and throughput, because we are allocating more and more information in memory to have it readily available, so that we don't have to recalculate that information over and over, and we can go faster. So this is just to show that you cannot always optimize in all dimensions. You need to pick the ones that are more important for you. So before you start optimizing, make sure you understand what kind of trade-offs do you want to make and what are the most important goals for you. And the next tip is always observe. So once you have developed the application and you have it running, you need to make sure you can keep looking at it and see how it's performing. And what I mean by that is not in your dev environment, but in your production environment. And because only in your production environment, you can get realistic traffic and see how the application responds to that particular type of traffic. Locally, it's very hard to create realistic environments where you can see the application behaving exactly as your user are seeing the application performing. Now, how do you observe an application in production? There is no shortage of tooling. There are open source and professional tools. Here I listed some of the open source tools that you can use for log, metrics, and traces. But if you use, for instance, AWS or Azure, there are tools, for instance, in AWS CloudWatch, which will give you all these different functionalities for you already available in the cloud. So make sure you learn those and use them. What could be interesting here to clarify, just very briefly, is what is the difference between logs, metrics, and traces, and why they are important in the context of performance. So with logs, generally, you can basically report events that are meaningful for your application. And literally for every single request, you can log what's going on in the application. So if something goes bad, you can literally start to read the logs and try to make sense of it. And it's generally a good practice to use structured logs. So where you, rather than just logging plain text, you log like objects in JSON, so that you can use tools that allow you to run queries and maybe filter by particular properties of the objects that you are logging. And you can do that, for instance, with Elasticsearch, or you can do it with CloudWatch logs. And this is a very important feature of basically every system that is running in production. The next topic is metrics. Metrics are something that you can look a little bit more in aggregation. So the idea of a log is that you can literally look at a single execution and try to make sense of what was going on. Metrics are more, I want to understand how the system is performing overall. For instance, with metrics, you can see what is the average CPU, or what is the average number of requests per second over a period of time, or even more business relevant metrics. For instance, I don't know how many users are currently logged in the platform. So you can store all this information as you see it, and then you can do queries to see at a given point in time what was the system doing in average or overall, not per request. Traces are another interesting concept that are somewhat in between logs and metrics. They are more useful when you have complex distributed system where you have multiple components and you want to understand for a given request what components are being involved to answer that particular request, and what is the impact that every component is having on the total time to answer to that particular request. Just to give you an example, you have an API. In that API, maybe you have an API gateway, then you have your backend. Your backend maybe needs to call a database, and at the end of the day, you get data from the database, you create a response, you send it back, the API gateway sends back the response to the user, and you have this entire flow where all these three components are working together to basically create a response for the user. And you might want to know, okay, what is the impact of the API gateway? What is the impact of my code in, let's say, a Lambda? What is the impact of running a query in the database? How long does it take? With a tracing system, you can see exactly what are the different components involved and how long every component is taking. So you could find places where you can optimize. Maybe you can notice the database is not fast enough, or maybe your code is not fast enough, or maybe API gateway is not performing as expected, so maybe some configuration to be tweaked there. Okay, the next tip is probably the most important one, is scale your architecture. Like sometimes we think a lot about the raw performance of an application, but in the cloud, I feel it's more important to think about the overall architecture if we care about scalability. And the reason why I say that is because performance is actually different from scalability. So far, we've been discussing about performance, but in reality, in the cloud, I feel we care more about scalability. And if you remember the definition that I gave you at the beginning, the main question that we need to ask ourselves is, how can we scale a system by adding resources, not necessarily by trying to make the system better and better, but we need to be able to scale the system by adding new resources. And the reason why we need to think this way is because, of course, we can optimize something and make sure we use the resources as best as we can, but there is a limit to that. Like at some point, we can only make a server so fast. What do we do if there is more and more traffic coming in? Like that server eventually, that server alone is not going to be able to cope with the increasing traffic. So we need to build an architecture where we can add copies of, for instance, of that server so that we can distribute the traffic across multiple instances of the same server. So when we start to think this way, we're thinking more about an architecture and how to scale that architecture to satisfy the increasing needs of our particular application in the cloud. And there is a tool that I really like that is allows us to see what are the different characteristics of an architecture in the cloud and how can we scale in different dimensions. It is actually called the scale cube because it is used to explore 3 different techniques, and they are represented as the 3 different dimensions in a 3D space. So the first one is the x-axis that represents the technique of cloning. Then we have the y-axis that represents the technique of functional decomposition. And then we have the z-axis, which represents the technique of partitioning. I didn't invent this idea. This is defined, or at least the first time I saw this concept was in this book, The Art of Scalability, which it is a book I really recommend. It is not the newest book in the market. It actually has been there for a long time. It was written by some of the engineers that scaled eBay. So for internet's time, this is very old times. But surprisingly, all the techniques that they explain, they are still very, very relevant. It's still used a lot today in all sorts of architectures in the cloud. And also what I really like about this book is that it's not only a technical book, because it also shows you that in order to be able to scale an architecture, you also need to understand how the organization needs to scale accordingly. So how to organize the teams, how to make sure the manager are understanding the goals. So this is a book that if you want to become an architect in the cloud and you want to learn all the tricks about scalability that you will need to use every day, not just technically, but also at an organizational level, this book will give you a lot. So it's really a recommended read. Okay, now I want to start to show you a little bit more in depth what the 3 different techniques actually mean and how we can leverage them in a Node.js application. So the first technique, as I said, is the cloning technique. And Node.js is actually very interesting because you can apply this technique in 2 different ways. The first thing is at the application level. So that basically means inside the same server, because Node.js is single-threaded, what you could do if you have multiple core available in that virtual machine, you could spin up multiple copies of the same server inside that of the same HTTP Node.js application server inside the same virtual machine. And then if you just put a reverse proxy in front of it, that is a way that allows you to maximize the usage of the resources available or the cores available in that virtual machine so that you can use the most out of a single virtual machine. Then, of course, we want to be able to clone also every single virtual machine so that if there is more and more traffic coming in, we can add more and more virtual machines and be able to deal with ever-increasing traffic. So inside one machine, we generally use a reverse proxy to be able to forward the traffic to all the available instances. But of course, when we have multiple virtual machines, we need to put a load balancer in front of those virtual machines. And the load balancer will make sure to distribute all the incoming requests collect the responses, and send them back to the users. So this is how the cloning technique works. How can we implement it in Node.js? If you want to implement the cloning technique inside the virtual machine, so by just creating multiple instances of the same HTTP web server, there is a module that is built in Node.js that is called the cluster module. And the way the cluster module works is that basically it's going to use multiple processes. You are going to have a master process, which is actually the one listening for incoming requests. And then for every incoming request, there will be a pool of workers that are basically sub-processes that are managed by the master process. And every sub-process is basically a copy of the entire logic that we have in our main HTTP server. And what the cluster module is going to do, every request that is going to coming in is going to be forwarded to one of the available workers. And then new request comes in, they are forwarded to other workers. And eventually, when we have responses, the master node will collect those responses and send them back to the users. Now, the one thing that I really like about this approach is that it's really, really easy to use. What we need to do is just write a little bit of wrapper code. So what we need to do is we import the cluster module. Then, based on the number of CPUs available in the system, for instance, we can decide to spin up more worker nodes. And what we do is basically, if this is the master, we'll need to have the logic that spins up all the worker nodes. Otherwise, in the else branch, we write the code that is the one that is actually dealing with the logic. So the one implementing the business logic for our web server. So this inside the else branch, we will literally have a copy-paste of the code we saw in the previous slides. But when we are in the master process, what we want to do is literally for every CPU, we are just going to call this function called cluster.fork. And that function is just going to spin up a new worker and attach it to the cluster. So this is literally all you have to do. And just by doing this, you're going to be seeing from 3 to 4 times more raw performance in terms of requests per second. And this is, of course, in an 8-core machine. That really depends on how many cores you have available. You can also use worker threads. This is relatively new in Node.js. And there is an interesting library called Piscina that you can use. And this library will give you interesting patterns that can be used in a similar way as what we saw with the cluster module. The difference is that if you use worker threads, there are ways that you can use to share memory between processes. Instead, when you use the cluster module, every worker is somewhat independent. It's an independent process. You are not allowed to share memory. So if you need to communicate between processes, you need to do it through different ways, like message passing, or using, I don't know, shared instances of a Redis, things like that. So this is just another option that you might want to consider for different use cases. I'm not really sure if there is a big difference in terms of performance. This is something that might be interesting to explore. Okay, cloning is probably the easiest strategy to scale a service, but there is a caveat there, as long as your application is stateless. Just to give you an example, if you have an application that requires the user to log in to do anything, what generally happens is that there is a user flow where the user is, I don't know, maybe inserting a username and a password. Then the system recognizes that user throughout the rest of the session. And generally the way that works, if you implement it in a simple way, is that you're going to have a dictionary or an hash map in memory in the process where you say, okay, for this particular session ID, I know that this session ID is user Luciano. So the next time I'm going to see that session ID in a request, I know that is Luciano that is still logged in and is still doing something. Of course, that means that our particular server is stateful, because if we are keeping that particular map of a session ID and a user in the memory of the process, that means that every single process recognizes a particular group of users. But if that user ends up logging in into another server later on, the session is not going to be the same. So you might end up in a case where a user is logging in, doing something, then visiting another page after a few seconds, and the user is not logged in anymore because landed in a server that didn't have the same state. So this is generally a common problem when you start to use the cloning technique. that you need to be aware of how to make every single process stateless. And that generally means rather than storing state information in the same process, you need to store it externally, for instance, in a Redis instance or in a database, so that every single instance or every single process will have access to the same shared state rather than having their own individual state. So this is what we mean with stateless. And once you do that, it gets very, very easy to apply this technique. There are other techniques, as I mentioned. Another one that is very common is called functional decomposition, but it is more common as microservices. And just to give you another example, imagine that you are building, I don't know, let's say an e-commerce, and in an e-commerce you might have two different functional areas, one that allows you to visit different products, and another one that allows you to manage a cart of products that you might want to purchase. And if we use functional decomposition, we could build these two different areas as two totally different and independent applications. And then we could use, for instance, an API gateway to be able to expose an entry point that can go to either one or another application. So if you're interested in products, you're going to end up in the products application. If you're interested in operations that involve your cart, you're going to end up in the cart application. An interesting thing about microservices is that generally the best practice is that every application will have its own dedicated database so that you can scale also the data storage independently from the other applications. For instance, here we're going to have a products database and we are also going to have a cart database. Now, what's pretty cool about this technique is that nothing is stopping you from combining functional decompositions or microservices with the cloning technique that we explored before. So that basically means that if you start to get a lot of traffic in the cart, for instance, service, what you can do is you start to clone the service application. And similarly, you can do the same for the products service. So in this way, we are combining the best of the two approaches, and we are getting even more scalability. Every application scales independently, and we are able to route the traffic to the proper backend and satisfy that increase in demand for that particular service. Now, my opinion is that Node.js is great for microservices because the whole philosophy behind the Node.js ecosystem is to do small things that work really, really well and combine them together. And this is pretty much the same philosophy you have when you deal with microservices. So you're going to find that all the libraries and the ecosystem help you a lot to build small services that do one thing and do it very, very well. Another interesting comment about microservices is that they can help you a lot in terms of scaling an organization, because if you are hiring more and more developers because your application is growing and you need to fulfill different use cases, then once you have microservices, you can start to divide ownership across different teams to different services. So generally that helps you a lot because you are not going to end up in a case where for instance, a team is blocked by another team because they're trying to work on the same piece of code and they don't really know how to prioritize those changes. And you have conflicting changes at the end of the day. When you have different services and different teams taking care of different services, then all this kind of conversations become a lot easier and every team can work a lot more independently. Okay, another thing to mention about microservices is that microservices are not a silver bullet. They add complexity. And so they have to be used with caution. Like you need to use them only if you really need microservices. If you're starting a new application, you're starting very, very small, probably you don't need microservices. Probably if you go for microservices straight away, you're going to build more complexity than you need. And you're actually going to make your life harder rather than easier. And just to give you a few ideas of what I mean by that is that when you start to deal with microservices, observability becomes more complicated because you have more moving parts. Deployments become more complicated. What do? Do I deploy this service first or this other service? What if the two services need each other to do something? They are maybe tightly coupled somehow. That's maybe not a good practice, but sometimes in practice it can happen. So how do you start to coordinate deployments for that? And one way of solving this issue is that you might start to use versioning, but being able to manage different versions or have different versions of the same application running at the same time is another complexity you need to deal with. And finally, how to integrate all these things together. It makes things even more complicated. So don't just go for microservices unless you realize you really need them. And now I'm going to try to finish the talk by showing you the last architectural scalability technique from the Scale Cube, which is called partitioning. And partitioning is more used to kind of scale data storages. And of course, databases, they also have limits. And in order to scale a database, the only thing that we can do is, rather than using a single database, we can try to use more than one database and spread the data across the different databases. So partitioning allows us to do that. And one simple example is, let's say that we have millions of products and our database doesn't scale anymore. What we could do, this is very naive, but it's just to give you the idea. We could say, okay, all the products which name starts with a letter between A and L goes to the first database. All the products that goes from M to Z will be in the second database. In reality, there are more complicated sharding techniques, but this is just to give you the idea that you can deterministically know in which database you need to look for if you're looking for a particular product. So partitioning is the last technique because it's generally the last one that you are gonna reach out for, because generally it's the more complicated one and generally requires a lot of planning. But also you need it only if you are at a very, very high scale and processing a lot of data and a lot of requests. And there is also another way of seeing partitioning that could be, for instance, for SaaS software, when they have a lot of customers worldwide, sometimes they replicate entirely their architecture in another region. And that's another way of seeing that idea of partitioning, where you start to collect data for different customers in different geographical regions in an architecture that is only present in a particular region. So everything is the same, just the data is distributed geographically. Okay, to try to summarize what we discussed today, the first tip is establish a baseline. You don't know how more performant you can make an application if you don't have a starting point. Then once you have a starting point, you need to find what are the things that makes the most sense to invest my time on and try to figure out if I can improve them. And you can do that only if you find your bottlenecks. So find what is the single thing that where the application is spending the most time, because chances are that if you can improve that, you're going to have a massive return of investment for your own time. Don't spend your time trying to optimize randomly, because most likely you're going to be able to optimize things that don't really make a lot of a difference at the end of the day. Then you need to understand your goals. We say that there are trade-offs to make. So only if we know what kind of goals do we have, do we care more about requests per second or do we care more about memory? If we decide that, then we can understand what are the different techniques that we can use and what are the different trade-offs that we can make things, to reach our goals, basically. Then always observe. Don't stop once you have something that you think that works. Make sure that you have ways to keep observing that application in production, because chances are that once it's running in production, you're going to be able to notice new problems or new opportunities for improvement. And finally, don't focus only on scaling that one server application. Think more about, how do I scale an architecture? Things are running in the cloud. We can avail of a lot of hardware given to us as a service. We can scale elastically up and down. So it's very important for us to start to think about scalability that way and to learn the techniques like cloning, decomposition, and partitioning so that we can scale applications in the cloud. And that's all I have for today. So thank you very much for being with me. And as I promised, if you go to this link, you can get the slides and you can see all the code examples and you can see all the other links for going more into depth about the various topics. So I don't know at this point if we have any time for question. I think we have about 15 minutes, so I'm more than happy to take any question. Okay, so I see the first question here. So thank you for highlighting it, and thank you for the question. So what will be the scope of Node.js when compared to other contemporary technologies? I'm not sure what you mean, but I'm going to assume, and feel free to ask more clarifying questions if I'm not replying to your question. But I'm going to assume that you mean something like, how does Node.js compare to other similar runtimes or languages? For instance, I don't know, I can mention about Java, I can mention about, I don't know, Python or other technologies like that. So this is generally a very opinionated type of conversation. So definitely opinion is important. Like, what I mean by that is that if you are working with a team that is very comfortable with JavaScript, I think Node.js is a very, very good choice because people will be immediately available to contribute. They don't need to learn a bunch of new concepts. But also what I would say is that there are other characteristics of the runtime that are very interesting. For instance, Node.js is very efficient in terms of when you have IO-bound type of workflow. So for instance, when you are writing servers that they don't do a lot of CPU-intensive work, but they mostly do coordination between a database, a file storage, and the network, then Node.js is particularly efficient because with the event loop, is going to be able to handle multiple requests by using only one thread. And that's why we can see very, very good performance for a language that is effectively an interpreted language. It's not a compiled language like Go or Rust or C++. So I don't know if I'm answering your question, so feel free to ask more questions to clarify what you meant. But yeah, I will go with Node.js if it's IO-driven type of application, and also if the team already knows JavaScript. Okay, there are other two questions. One is, for a beginner, what will be the recommendation to get started with, or for Java professional to change the domain? What will be the process? So I don't know if you are meaning that you maybe already have a Java application you want to migrate to Node.js, or more, what do you need to do if you want to learn about Java? I suppose I can try to answer both. Regarding Java, I'm not a Java expert, so I wouldn't be the best person to recommend resources to learn Java. So I'm going to leave the question out. Regarding how do you migrate from, for instance, from a Java application to a Node.js application, I don't think there is like a always valid answer. It really depends from the application itself. And I would actually discourage, for the most part, to do this kind of migrations unless there is a very, very strong reason in terms of business needs or performance or something like that. I would prefer to apply a strategy like the strangler pattern, where rather than rewriting the entire application for instance, from Java to Node.js, maybe you can only write small portions of the application one at a time, and then you can have like a proxy in front of your application that understands which implementation has what, and it's going to route the traffic to the new implementation only for the components that we have re-implemented. By doing that, you can see a return of investment much, much early on. You can see if there is a performance benefit much early on. And sometimes you'll even find out that it's not worth continuing the experiment. So you haven't invested a lot of time in migrating an entire application to another language, because at some point you realize it's not worth it, so you can stop early. If you do like a big bang release where you rewrite everything and then you just swap, sometimes you have invested a lot of time, energies, and money, and then you realize it wasn't even worth it. So it's always risky to go with a full-blown rewrite and deployment. Okay, we have another couple of questions. Before starting to think about how the architecture could scale, maybe it's better to think about the API. Exposing an API for creating the QR code and another one for fetching could be better. That's a very good point. Thank you, Tommaso. I think that's in line with the idea of microservices as well, where maybe creating a QR code could be a service that is available in our architecture. And then at that point, we can think about that particular service more in isolation. We can think about the performance of that particular service on its own without coupling it with the other services. And that is an interesting way of dealing with some scalability challenges, because then at that point you can start to think, okay, how much is this service going to be used by other services? You can make an estimate, you can look at historic data and say, for instance, we need to be able to support X amount of requests per second. And at that point, you can go back to the architecture and the implementation of that particular service and see what you can tweak to be able to support that particular need. So decomposing things into services make things easier, because you can reason about the problems at a more granular level. All right, next one. Thank you, Sasa, for the question. What do you think about the future of Node.js? Node.js versus Go, Rust picking more parts of Node.js work? That's an interesting question. I admit I've been spending a lot of time lately looking at Rust, and I'm actually really enjoying Rust as a language. I think Node.js is still very, very relevant in the market. It's still an amazing tool that allows you to prototype, but also run production-ready applications very, very quickly. And what makes it particularly appealing to me is that if you're building a web application, most likely you need to build a backend and a front end. In the front end, 99.9% of the times you need to use JavaScript, because it's very hard to use anything else. So at that point, you have a huge knowledge of JavaScript already. Why not using it also on the backend? This is, to me, one of the winning characteristics of JavaScript and Node.js for full stack applications. But of course, there are use cases where maybe you have to do CPU intensive work. And in those cases, it could be more convenient in terms of performance to use compiled languages like Go or Rust. So there is definitely space for that. And of course, the two are not excluding each other. Again, you can use microservices and only build that one particular service in Rust, because you need an extreme high level of performance for that one particular server. But for everything else, you can still use Node.js, and maybe it's going to be fast enough and performant enough. And also it's going to be easier to build something in Node.js than it's going to be in Rust, most likely, unless you're really, really skilled with Rust. Okay, next question. Worker threads or child process for computing tasks? I think that really depends. I think you could probably use both, and it depends on the libraries that you use. You might have APIs that are more or less suitable to your needs. The main difference will be that if you use child processes, then every process has its own memory, and the only way you can share information between processes is by sending a message. Now, most of the time that's good enough, and that's also convenient, because not having shared memory makes every single process safer and easier to reason about. But sometimes if you are processing a lot of data, it could be convenient to just have a number of workers that share the same memory and they work together with the same memory. At that point, worker threads, I think, will give you that capability. I haven't done a lot with them, so maybe I'm missing something important there. I'm just going to caveat that. But in general, yeah, with worker threads, you have this additional capability, and it might be useful for you. So in that case, you need to go with worker threads. Okay, I don't see any other question. Oh, new question, okay. How to find whether a process created a V8 instance or not? I'm not sure I understand the question, because a Node.js process is always running on V8. So there is always V8 that is interpreting the Node.js code. So unless you have an abstraction on top of the processes that run, and sometimes you can run Node.js processes and sometimes you can run other things, when you run a Node.js script, you are always running it through V8. Okay, because we are getting close to the time, I'm going to remind you that you are more than welcome to connect with me. You can see my Twitter handle there at the top right corner of the slides. Feel free to ask me questions even later, tomorrow, the next few weeks, if you can think about new things. If you end up buying the book and reading it, please remember to give me some feedback, because that's the only thing that can help me and Mario to make sure the next edition is going to be even better. And yeah, I just want to say again, thank you very much, everyone, for having me. It's a huge honor, and I hope that this talk has been useful for everyone. I'm gonna be waiting for the host to join. I will need to go in about a couple of minutes. So let me know if I just need to leave the studio or